So let's explain what is Gauss's law for. Well, the short answer is to calculate the electric field strength. And I'm emphasizing the word strength because it's to calculate E, not E vector. What's the difference? That's the magnitude. That's the lazy way of saying the magnitude of the electric field vector. So electric field strength, electric field vector. Okay, make sure you understand the difference as well. Namely, for example, this is always positive. The magnitude is the length of a vector. All right, so let's say you want to calculate electric field strength. There's two ways to go about it. You need to ask yourself, are you calculating a point charge or are you calculating for not a point charge? If it is calculating for a point charge, you want to find the electric field strength here, some distance away. You already know the formula from last week. You plug in the distance over here and the charge over here. That's the formula for it. However, if it's not a point charge, for example, if it's a line of charge, if it's a sphere, or if it's something more complicated, if it's a sphere within a sphere or within a point charge, or it's a plane of charge, never use this formula. That's not applicable. That is for point charge. So you put the point charge over here. And for this side, what you need to do, if you need to find, oh, I want to find the electric field here. What is the field strength over here? The only solution is to use Gauss's law. I'm going to write it a few times because first thing I want you to do is to commit that to memory to properly learn this and also have comma S and define S on the left-hand side. All right, so let's do a quick example. Let's say I have a charge in the middle, which is minus Q, and then here there is a charge of minus 2Q, and then here there's another thin shell. So these are just very thin metal shells. Thin means there's no thickness, and let's say that's positive 5Q, something like that. And I want to find the electric field strength somewhere between here, okay, in between these two layers. So how do you do it? First step is draw the electric field lines. So there's 3 steps you go through, and it's very repetitive. So make sure you learn these 3 steps, and then you know how to solve it for all electric field problems. The first step, you draw the electric field lines. So because it's so symmetrical, you know that the electric field lines are going to be radially diverging away from the center. The next thing is the field lines, you need to put in the arrow. Remember how you determine the direction of the field lines is you imagine a positive charge and which way it'll go, right? So let's zoom in this region first. This is minus Q to negative 2Q, right? So if you have a positive charge, which way will it go? This side is negative Q, this side is negative 2Q. So this is more negative. It's going to attract a positive charge. Well, technically negative, it will be torn between both sides. But if this is more negative, it's going to attract this way, right? So here, the direction of the electric field lines is going to point radially outwards like this. And then how about in the middle? Again, ask yourself a positive charge, which way will it go? Well, this time it will go this way, right? It's going to repel from this surface and going to attract to this surface. So on this region, the electric field lines are going to point inwards, and then on the outside, you can conclude yourself that the electric field lines are going to point outwards. So this is your configuration. That's the first step you do. The second step is recite out Gauss's law. Notice I have write down the surface over here. So what is S? S is the Gaussian surface of where you want to calculate your electric field strength at. So I want to calculate it over here. So I'm going to draw a surface like this and call it S. So that will allow me to calculate the electric field at that point, okay? And what do you do? So now you have the left-hand side and the right-hand side. The right-hand side is easier. So let's start with the right-hand side. I'm going to first copy exactly out. The first step, just copy it out. It's a simple step. Everyone can do that. Then you ask, what's the charge enclosed inside S? What is the charge enclosed inside S? So you see the value of writing down S because now you know what to take care of. Well, enclosed inside is this amount of charge. Okay, so you have your answer here. And then you do your left-hand side. This is probably a more scary bit. So let's break it down. The first step, copy it, copy everything. The second step is the vector. It's the most complicated thing over here. You only have one surface, so you don't have to break up this integral into several pieces, and you only have to deal with the vector. Now, the vector, you need to know the rule of dot products. There's only 3 options. If they are parallel, if the 2 vectors are parallel, it's just A times B. If the vectors are anti-parallel, the minus AB, in general, it's AB cosine theta, where theta is the included angle. Now, you need to ask yourself, which case is this? Is these 2 dot product parallel, anti-parallel, or general case? Well, where are you looking at? Looking at S. So that's the importance of having the S over here. So let's zoom in over S over here. Well, where is the electric field vector pointing at S, on the surface of S? Well, it's pointing radially inwards. So the electric field on S is pointing there. How about dA? dA means a little piece of area, right? Remember, D means little piece of area over here. How do you decide area vectors? Area vectors is always decided as 90 degrees from this little area pointing away from the center of that area. Okay. So the area vector is pointing this way, the electric field at the point of interest on S. I don't have to pick this point, basically any point on S. You see that E is pointing this way, whereas the area is pointing that way. The area vector is pointing that way. So they're always anti-parallel. So if they're anti-parallel, the answer is, it's just minus EDA. And then you ask yourself, can I pull E out? Is it constant? No, E is not constant because E, the further away you are from the surface, E is going to be weaker. As closer you are to the middle, the electric field is going to be stronger, right? If you're very far away at infinity, it's going to be very weak. However, on S, it is constant. So as far as the integral is concerned, you can pull it out. So don't be mistaken that E is a constant. E is not a constant. As you see at the end, E will depend on the radius. But as far as the integral is concerned, it is a constant. So in this case, you're allowed to pull the E out. Now what you're left to do is just do the integral. What's integrate dA? Integrate dx is x, right? So integrate dA is a. A of what? The surface. Notice the beneficial point of having the S labeled. What's the area of the surface? What surface? Surface S, right? What's the area of a sphere? 4 pi r squared. Well, I need to define what's r. Let's assume I had done that. It's asking for distance r. So 4 pi r squared is the area of the surface. So now all you have to do is just to match up your left-hand side to your right-hand side, combine these two together. So you have negative E4 pi r squared equals to minus 3q over epsilon. What is your aim? Your aim is to find the electric field strength, which is minus 3q over 4 pi epsilon r squared. Okay, so, oh, sorry, positive 3q. So this is your answer. And notice it is positive as it should be because electric field strength, right? Magnitude of a vector is always positive. If you ever get a negative answer, you're doing something wrong. So that's a good sanity check. So that's how you calculate the electric field over here. If you calculate the electric field over here, you do a smaller Gaussian surface, draw your Gaussian surface wherever you are interested in calculating the electric field at. Okay, so that is electric field. How about potential? What's electric potential?